All right, so our primary purpose today is we want to kind of kick off where we were on after yesterday. We were starting to look at the difference between stable and radioactive isotopes. And I promised you something I haven't delivered on yet, but I'll show it to you here because I have it. It's just in another so this idea of stability, this is the graph I was referencing yesterday. This is the band of stability. So this series of black dots represents stable nuclei for, well, basically any stable nucleus. And the point of this black line here is just kind of a quick reference to where are the one-to-one ratios. So where do we find equal numbers of protons and neutrons? And so what we can see is that, again, up and through element number 20, this band of stability stays pretty close to this black line. But in here around 20, you can see that it definitely starts to curve upwards. And what we will find, if we look at this further, is, again, the last known stable isotope is bismuth, element number 83. And so you are going to find that those different modes of radioactive decay that we were looking at have a lot to do with whether we have an isotope that is above the band, below the band, or ahead of the band. The ones that are ahead of the band, where our atomic numbers are greater than 83, we tend to see alpha decay in a lot of those. For the ones that are up higher here, where we have too many neutrons, we tend to see beta decays in those cases. Up here, where we have too many protons, we tend to see positron emissions instead. And gamma rays, well, that's something completely different in and of itself. So with that in mind, now we can look at these individual types of radiation and get a little bit more of a sense of what they are. So, for example, an alpha particle. An alpha particle, we know by the fact that it is extremely heavy. It's got basically the foundations of a helium atom. It's got 2 protons, it's got 2 neutrons. The only thing that's missing are the 2 electrons. That's the difference between an alpha particle and a helium atom. The alpha particle has no electrons. Beta particles, on the other hand, these I mentioned a little bit yesterday. These are very similar to electrons. They have virtually no mass because, again, think about the difference in mass between a proton and an electron. Protons are so much more massive that we basically consider electrons to be massless. But we've got a -1 charge on it because electrons are negatively charged. And so the type of notation that we see with these, we can see them shown in this way where they kind of have their elemental or subatomic kind of look. We can also see them with their Greek letter look as well, where we've got the lowercase letter alpha here instead of helium, the lowercase Greek letter beta instead of electron. And then if we take this further, we can see that positrons look very similar to beta particles. You see really the only difference between them is in their charge. They have 0 mass, but a +1 charge instead of a -1 charge. You will often see them with the beta notation as well. Sometimes you will see beta positive like this to indicate a positron, and beta negative to indicate a negatron, or what we traditionally call a beta particle. Gamma rays, this is the only way that we signify a gamma ray. It has no mass, it has no charge, it is pure energy. And so one of the things that we talked about yesterday is that there is this relationship in radioactivity between mass and energy, and it's an inverse relationship. The heavier the particle is, the lower energy it's going to be. The lighter it is, the more energy it's going to have instead. And so obviously, if I have something that has no mass whatsoever, it's going to have the most energy of all. Now, where do these come from? These come from what we call annihilation reactions. I've got two antiparticles. The beta particle, which is negatively charged, and the positron, which is positively charged. When these two antiparticles collide, then resulting nuclear reaction is what gives us gamma rays. And so just kind of summarizing, we can see that in addition to the particles themselves, some of our subatomic particles can also be shown using this notation. So the proton and the neutron can also show out in this way. The proton can be shown out as a hydrogen nucleus, hydrogen without the electron. It can also be shown as, oops, that would be 1,1 proton. Again, remember, the number on top is the mass number, so total number of protons plus neutrons. The bottom number is the number of protons. You can also think of it as kind of the charge of whatever it is, since all of these subatomic particles here are being represented as being without electrons. And so where the protons and neutrons come in is there are some nuclear reactions that are going to produce either a proton or a neutron as a consequence of the nuclear reaction. We'll see that especially when we look Thursday at nuclear energy processes, fission and fusion. Those tend to involve a lot of neutrons and sometimes protons coming together. The other thing that we see often is with these beta decays, whether they be beta particles or positrons, what we see inside of the nucleus is basically a switching between a proton and a neutron. So in beta decay, you see a proton turning into a neutron. Or I'm sorry, you see a neutron being turned into a proton in beta decay. In positron emission, you see a proton being turned into a neutron. And so in all of these cases, with the exception of some of the gamma decays, in all of these cases, usually what we see in addition to the radiation is a change in the identity of the nucleus itself. Because if we're seeing either parts of the nucleus breaking off or the composition of the nucleus changing, proton to neutron or neutron to proton, suddenly we don't have the same nucleus anymore. It's going to have a different number of protons. It's going to be a different element as a result. So one of the things that we're going to be looking at in both today and Thursday is the idea of what happens when we're exposed to radiation. Radiation is said to be ionizing. And what that means is that when we encounter radiation, that radiation is going to disrupt the number of electrons that are surrounding our atoms. So the stuff that makes us up, exposure to radiation is going to knock around some of the electrons that make up our atoms, that make up our bodies. And in the process of knocking around those electrons, we get the formation of these unstable ions. And if there's one thing that I can teach you about chemistry in general, is that when something is unstable, it's going to do something to become more stable. So when your cells become unstable, they're going to go through some kind of process to get to a more stable state. Now, unfortunately for you, that usually means bad things in terms of your health. Because if you've got skin cells that suddenly have had their electrons knocked around, those skin cells are going to start reacting to kind of try to fix the problem that was created by the radiation. Problem is, the easiest means of fixing it is usually doing things that we don't want, whether it's things like formation of cancer cells or even just simple things like the formation of point mutations or moles or other kinds of things. Sometimes the effects are relatively harmless. Sometimes, as we know, those health effects can be quite dangerous. So in addition to those, we can see that those ionized substances, whatever they are, can also knock around water molecules. In knocking around water molecules, we now have an unstable water molecule, and that can cause some other chemical reactions to take place. Obviously, where this is the most dangerous to us are in the places in our body where we undergo the most change. So this is things like, skin cells, especially. Our skin rapidly regenerates and reforms itself continually. But if we want to look at other places, things like your bone marrow or your reproductive cells, those cells, because they are in constant activity, tend to generate constant activity. And so if there is a mutation or some kind of other problem inside of those cells and they replicate, now not just do you have one bad cell, but now you have a bad cell that is reproducing itself. And depending upon what kind of reproduction it is doing, you can get all sorts of interesting and nasty effects. So how do we protect ourselves from radiation? As I said yesterday, radiation is around us at all times. We are currently being hit with radioactive materials. Now, the dosage is not that large. Chances are pretty good that we're not going to have any kind of ill effects from it, but we are still being hit with radioactive particles right now. So what does that entail? Well, to protect ourselves, usually the best way to protect yourself against radiation is to don appropriate And for the kind of radiation we encounter the most, alpha radiation, that just means taking good care of your skin, wearing appropriate clothing. And appropriate clothing really just kind of means any clothing. Clothing itself will block alpha decay, will block alpha particles from penetrating your skin. Your skin overall does a pretty good job of blocking it as well. But if you have like open cuts or other means of accessing your internal systems, obviously that creates other problems for you as well. Now for beta decay, because it's a little bit more energetic, it's going to require a thicker, denser material to block its penetrating ability. So generally we're talking about things, thicker fabric materials, certain kinds of metals in various thicknesses. So, relatively thin, not aluminum foil thin, but a thin layer of aluminum, like aluminum sheeting, which is around most of this building. That's usually enough. For gamma rays require a lot. And in that field of gamma rays, we can also think about other kinds of similar radiation like X-rays. For that, you need usually several inches, if not more like feet, of either concrete, feet if we're talking concrete, or several good inches of lead, if we're talking about that. So this explains why when you go to the dentist and they take pictures of your teeth, they put that lead vest over top of you. Why do they do that? Well, the lead is enough to block the X-rays from attacking your internal organs. Now, why do they at the same time also run behind the wall? Well, it's a dosage thing in their case. Instead of just getting a brief couple of second exposure like you are, they're taking pictures of people's teeth day in and day out. They're going to get exposed to a lot more. Running behind that wall puts that extra barrier between them and the radiation. Other ways that you can protect yourself against radiation, two things. Dosage. If you're not around the radioactive material, you're not going to get exposed to radiation. Sounds pretty straightforward and simple, right? The other thing is something called distance. With distance, we can think about something called the inverse square rule. What the inverse square rule tells us is that as we get further away from a radioactive source, the actual radiation that we experience doesn't just decrease by a multiplier, it decreases by the square of that multiplier. So what I mean by that is, let's say we have a radioactive source here, and at this spot here, 1 foot away, we receive a certain amount of a dose. We'll call that X. At 2 feet away, we're obviously half as far, or we've put twice the distance. But the amount of dosage, the amount of radiation we actually feel is actually a quarter of what it was that one step further. And at 3 feet, it would be 1/9, and so on and so on and so on. So, especially for the high energy stuff, but even for the low energy, the further you get away from the source, the less damage it's going to do, because the less effective it's going to be. That radiation spreads out in all directions. And so since it effuses in all directions, it's not one directional, that means that the further away you get out from it, it goes away a lot quicker. So this is called the inverse square law. I'm going to rewrite that. And basically all that it is saying is that if you double your distance away from the source, the radiation you feel is 1/4. It's squaring that distance. So if you triple it, 3 squared is 9. The radiation you feel is 1/9 of what it was at that original distance. You take it by a factor of 5. 5 squared is 25. Now the radiation is 1/25 of what it was at the original distance. So really, the more distance you put between you and a radioactive source, the better it is, the easier it is to get into what we would call that safe dosage area. Again, just kind of putting all of this in perspective here. So alpha particles, because their energy is relatively slight, we can see that their range of distance, how far they can actually travel, is not very far at all. So if you are near an alpha emitter, you've got to be really, really close to it to actually feel the radiation on it. And its penetrating power into your skin, 5/100ths of a millimeter, it barely penetrates. Common sources of alpha particles, things like radium, radon. And so most of our background radiation comes from those two things. Radium is found in some types of minerals and rocks, just things that are naturally underground that you really can't help at all. And radon, same kind of thing. Radon is the product of the alpha decay of radium, which is also why radon is one of those things you get tested when you move into a new home. You test for radon. The reason why is because of the fact that it's radioactive. With beta particles, we can see that difference in size and that higher energy does make it go a little bit further. You can see it goes anywhere between 2 and 3 meters in the air. And it can also penetrate up to 5 millimeters into your skin. So that's enough to break through that first layer of your skin and get into the second layer. Shielding for that, we talked about already. Carbon-14 is a common place where we find that. And carbon-14, you probably know best if you've ever heard of radiocarbon dating, how we test artifacts to figure out how old they are. That's the source. That's what we use for that. For gamma radiation, that high energy stuff, we're talking about 500 meters. So, half a kilometer, that's what, 0.3 of a mile, give or take. Tissue depth basically can go through you. 50 centimeters, that's what, about 10 inches? 20 inches. So yeah, it goes right through you. For that shielding, you need something that's really dense. Lead is a really dense element. That's why it's used for that purpose. Concrete can do the same thing if we pack enough of it and we make the barrier thick enough. All right, so let's look at this second section then. We're getting into the nuclear reactions, and I'll tell you, the majority of what you need to know for this chapter comes out of this section, because a lot of the things that we're going to be doing on Thursday kind of tie back to this original concept. We're just applying it. So what we're doing in these nuclear reactions is we are tracking what happens when radiation occurs. So let's say I've got that radioactive uranium nucleus there. When it undergoes an alpha decay, what happens? Well, that alpha decay is going to produce an alpha particle, and it's also going to produce this isotope of thorium, thorium-234. How do I know that that's what happens? Well, that's where nuclear reactions and nuclear equations are going to come in and kind of lay the groundwork for us. So some things that we need to know and things that we need to recognize. When we balance a nuclear equation, we need to keep track of the mass number and the atomic number throughout the reaction. Because overall, what we are going to see is that there is some equality in those two numbers if I compare the two sides of the reaction against each other. So, like we said before, we know that the mass number is going to change more than likely. We know that the atomic number is definitely going to change in almost every case. But what else? So if I look at this particular reaction that they are giving us, we have californium-251. Californium-251, we're talking about californium. Californium's atomic number is 98. And its mass number is 251. It's going to undergo a decay. Now we should be able to recognize this particle as an alpha particle. And so we would call this reaction alpha decay. But in this alpha decay, we are going to see that not only are we going to be changing the mass number and the atomic number, we're going to get a new element out of this as well. How do we identify that new element? Well, this is where our knowledge of atomic number comes in. If two of those protons that were in californium are now in the alpha particle, that means that there are only 96 protons left. Element number 96, I go to the periodic table, is Cm. Cm is curium. So in this alpha decay, not only did I eject this particle, not only did it come with a bit of energy as well, I've also confirmed that I have converted californium, which was unstable, into curium, which is also unstable, but that curium is more stable than the californium was. So an important note here, the products of these reactions may be radioactive also, but they will be more stable than the reactants were. And that's an important note to make. That's something that we want to log in our brains. Because it is important to know that every chemical reaction is going to do this in some kind of way. Our products are going to be more stable than our reactants are. And if they're not, then the reaction doesn't go. Good. Yeah. Yeah. Okay, so if we're looking at, you know, a radioactive sample like uranium or plutonium or something like that, the term weapons grade or nuclear grade, that usually has to do with the purity of it, how much other stuff is in that sample. Obviously, if you're building a large scale bomb, you want as much of that sample to be your plutonium as possible so that you get the maximum destruction when you cause that reaction to happen. So thorium would also be a solid. So yeah, so I mean, thorium and uranium, they're both somewhat naturally occurring. They both would be found in rocks. So we're talking about mineral deposits that are the raw materials that start most of those things. But as far as, like, you know, these products being more stable, they are. What we are seeing is this is much more likely to react and decay than this one is. Now, one of the ways that we measure that is with half-life, and we'll talk about half-life on Thursday. But the idea of half-life is how long does it take for half of this material to react? And if you've got something with a short half-life, obviously it's not very stable because it's going to react and react and react and react and react. If you have something with a long half-life, then that means that it is more stable. And so if I were to compare the half-lives of this uranium nucleus and this thorium nucleus, what I would expect to see is that, yes, both are radioactive, but that thorium nucleus should still be generally more stable, longer half-life, less likely to react. Now, it doesn't always work out perfectly that way. Sometimes what we have like intermediate reactions that take place where, you know, we'll get an alpha decay that produces some kind of substance that is kind of stable, but undergoes a quick beta decay to gain more stability in the process. And so sometimes we see those reactions kind of couple with each other. But generally speaking, what we start with in these radioactive decays is going to be more unstable, more reactive than what we end with. Otherwise, the process wouldn't need to happen or wouldn't happen very often on its own. So how do these equations look? Well, this is where we have to apply those very simple mathematical properties. So again, what we want to look at is equality. The mass numbers on both sides should even out. The atomic numbers on both sides should even out. So if I have 241 as the mass number here for americium, I know that whatever this mystery particle is plus 4 is going to give me 241. Now we just got to do a little bit of simple algebra. Subtract 4 from both sides. I'm going to get 237 as my mystery mass number. If I look at the atomic number, again, I've got 95 for the americium here. 95 is equal to our mystery atomic number plus 2. Subtract 2 from both sides. My mystery number is going to be 93. So my mystery particle has a mass number of 237 and an atomic number of 93. I look to the periodic table. 93 is NP, not on your list, but that's Neptunium. Easy way to remember that is just they go in order. Uranium, Neptunium, plutonium. That's the order of the last 3 planets, or at least, Pluto used to be one. But as far as these nuclear equations go, this is really all that you have to do. It's just a matter of very simple bookkeeping. Make sure that the numbers on top even out. Make sure the numbers on the bottom even out. Use that atomic number to figure out what the stuff is. So what is the new identity of this element? For beta decays, again, the same kind of idea we see. We have an unstable nucleus that is undergoing some kind of radiation. It's going to kick off this beta particle and energy. And the resulting product here, nitrogen 14, is actually stable, not radioactive at all. Doesn't always work out that way, but that's kind of the end goal. We want to look at radioactivity kind of in this broad sense. The end goal of radioactive decays is to get to a stable nucleus. Now, it might take 10, 20, 25 radioactive decays to get there, especially if you're looking at one of those larger synthetic elements. What was that? No. So for those bigger elements, I mean, yes, uranium, the process of turning uranium into lead takes about 20 decays. And that has mostly to do with the fact that the uranium isotope is just so big that it undergoes a series of alpha decays, but it then has to also undergo a series of beta decays to try to refigure that proton to neutron ratio to become a little bit more stable. And so it ends up taking between 15 and 20 steps to actually go from that unstable uranium to the stable lead isotope that it would desire to be. And along each step in the process, you've got many, many years of half-lives along the way. Now, when we're talking about nuclear power, or we're talking about bombs, actually the same concept pretty much prevails for both. What we're talking about there is a different process. We're not actually talking about a nuclear decay process. What we're talking about is an artificial atom splitting process where we bombard the nucleus with neutrons to get it from being not stable to really not stable. And in the process of going to really not stable, the atom basically just rips in half. And when it rips in half, it blows up a whole bunch of energy. That energy either goes and gets diverted to making electricity on one side, or gets turned into wide-scale destruction on the other side. But it's basically the same technology in both directions. All right, let's look at this one. Write an equation for the decay of potassium-42. Potassium-42 is a beta emitter. So I've got potassium-42 I'm going to need to look at the periodic table. Periodic table tells me potassium is element number 19. And so I know it's a beta emitter, which means that it is going to make a beta particle as one of the products of this nuclear reaction. The question is, what is that other product? And again, we have to look at our ideas of conservation here. So 42 is the mass number. I get nothing from the beta, which means that the unknown is 42 minus 0, or 42. That's the mass number of our unknown. And on the flip side, I've got 19 as being equal to -1 plus my mystery particle's atomic number. Here's where the math can get a little bit tricky. We're subtracting a negative number. When we subtract negative numbers, that's the same thing as adding. So if I add 1 to each side, I'm going to get 20 as my atomic number. So my mystery particle has a mass number of 42 and an atomic number of 20. I look at the periodic table, element number 20 is calcium. Now, is this form of calcium stable? Probably not. You probably would need to undergo another, probably another beta decay. Again, how do we know? We can compare the mass number to the atomic mass on the periodic table. Gives us a rough idea. Remember the atomic mass, the mass on the periodic table tells us the most likely isotope. So the most likely isotope of calcium is 40. 42 is a little bit bigger than that. It means we've got maybe a little bit too many neutrons. So turning a neutron into a proton, that would be a beta decay. All right, let's see how we're doing. Write the nuclear equation for the beta decay of cobalt-60. So go ahead and work on this yourselves here. Take a couple of minutes and see if you can come up with what does that nuclear equation look like. And after about 3 minutes, we'll talk about the correct answer. All right, it looks like we're on the right track. So for the mass number here, obviously we needed 60. We are getting nothing from the beta particle, so 60 will be the mass number of our mystery particle as well. And then the beta is giving us a -1, so 27 minus -1 is the same thing as 27 plus 1. So 28 is the atomic number. Atomic number 28 is nickel. So if I were going to write out the full equation here, it would look something like this. But obviously the beta and the nickel could switch spaces. Joel? I mean +1. Oh, minus -1. Yeah. It would be. It could be. The only reason I did it this way, the first couple of examples that we did, we ended up having to subtract by what was ever on the other side. So if I was subtracting this side by 2, because it was 2 here, I would be subtracting by -1, which again, it's the same thing as adding. You're right. All right, any other questions? All right, just a couple more examples to walk through, and then we'll be able to kind of work our way to the end of this first half of the unit. Positrons. Positron emission, very, very similar. Very, very similar to beta decay. The only difference is the positive one instead of the negative one. So instead of adding one to the atomic number, we would end up subtracting one to get the product on the other side. Fundamentally speaking, what we're talking about is the conversion of a nuclear proton into a neutron. So if we look at this from that standpoint, again, the mass number does not change in these beta style decays. Only the atomic number does. And this time the atomic number goes down by 1 because we're turning that proton into a neutron. So we're losing a proton in the process. With gamma radiation comes in a couple of different forms. The first form, we talked about the annihilation reaction. In the annihilation reaction, we've got the two pieces of antimatter, the beta particle and the positron colliding, and we get 2 gamma rays as a result. Another form is like this. This M here refers to something called metastable. And you don't need to know what that is. You don't need to write that down necessarily. Just know that basically it means that it's stable-ish. It's there for long enough that we can monitor it and we can see it, but it very quickly decays. And when it decays, it just pushes out this pure energy, and we get left with the more stable form of technetium-99. So this doesn't violate any of the principles that we were talking about. Remember, the whole idea of radiation in general is to increase the stability of the nucleus. This does so. We've got something that's high energy and, kind of sort of stable. It ditches that extra energy and becomes more stable in the process. Doesn't lose any particles. It's exactly the same atomically as it was when we started, but it's lost that extra energy. And in losing that extra energy, it has gained some stability as a result. So in summary here, of these 4 types of radiation, 3 of them are going to give us a completely new element. Alpha gives us a new element, beta gives us a new element, positron emission gives us a new element. What those new elements look like, well, it just depends on the type of radiation that we are looking at. And it's not something we really just have to memorize. It's more a matter of, can we follow the nuclear equations? That's why we work on those nuclear equations, so that we can kind of quickly monitor. Oh, this gave away an alpha particle. We're going to lose 4 in the mass number and 2 in the atomic number. Oh, this one gave up a positron. The atomic number is going to change by 1. And with gamma, all we're talking about is just increasing stability by getting rid of that excess energy in the form of a gamma ray. Now, moving on to something more along the lines of what Sean's been itching around at for the past 45 minutes here. How do we get to radioactivity? How do we get to some of these kinds of isotopes that can do other things other than just naturally decay and naturally occur? So radioactivity can happen through what's called bombardment. Bombardment is basically what happens when we shoot small particles at high speeds and energies at nuclei. Now, on a much more micro scale, if you've heard of what has been happening over the past 15 years in Switzerland with the CERN super collider, that's basically what they're doing, only they're using subatomic particles like protons and neutrons and electrons and shooting those things at each other as opposed to full-on elements. What? They've been doing a lot of very interesting physics stuff there. This is also the process that we used, or not we, I won't put myself in this mix because I had nothing to do with it and don't really understand it fully. But if you look at a lot of the heavy elements, all those ones on the bottom row of the periodic table, the ones that don't even try to have stable nuclei, all of those were created synthetically. If you look at the periodic table, the ones that have parentheses around their atomic masses, those are synthetic elements. They have no naturally occurring isotopes whatsoever, radioactive or stable. So, americium and californium, mendelevium, nobelium, all those are synthetic. They were made in a laboratory. And this is how it was done. What they did was they took some kind of nucleus and they bombarded that nucleus with other particles, trying to get those particles to stick or adhere themselves to the nucleus, cause a radioactive decay of some kind to generate a new element. And that's how we went from 93 elements to 118 elements. Most of that stuff that was done after your uranium was done in that form and fashion. On a smaller scale, this is what a transmutation is. You can see throwing alpha particles at this boron nucleus can turn that boron nucleus into nitrogen. Now, that nitrogen being radioactive itself, it's going to generate something else. My guess would be that it'd probably go toward carbon. But the thing is that we notice we can monitor and track these reactions using the same nuclear equation technique that we use for the other types of decays. Look closely. My mass numbers still even out. My atomic numbers still even out. Yes.
So why isn't the new radioactive nucleus, why isn't it just nitrogen 14?
The process of bombarding exerts too much energy on the nucleus that it can't stay together completely. It doesn't fuse fully. What happens is basically the resulting particle just has so much energy that one or more of those subatomic particles, usually neutrons, but sometimes protons as well, will kind of shake off the tree in the process.
How will we know whether one of the ones that shoots off is a neutron?
So they they'd have spectroscopy techniques that would be able to tell us what the atomic number and mass number of the particles that are falling off of this are. And so we'd be able to tell from that technique, oh, this particle has a mass number of 13 and this one has a mass of 1. Oh, and that mass of 1 doesn't have a charge. So we can kind of figure out what everything is based upon, analyzing the charges as they go through a detector and analyzing the masses as they go through a detector. So what this creates then for us is we've got an ability now that we can look at, well, what if we do this kind of a nuclear reaction? What if we do this kind of a nuclear process? What happens in the result of this? Well, we can adjust for it the same kind of way. Total atomic number here is 29. Total mass number is 59. And so if we go by elimination here, 59 minus 4 would give us 55. 29 minus 2 would give us 27. Element number 27 is cobalt. And cobalt 55, let's see, cobalt, we would expect somewhere around 59. So at cobalt 55, we're talking about a radioactive particle more than likely. So chances are pretty good that this cobalt would go through some other process along the way. And this time, since we are under that line of stability, we're probably looking at positron instead of beta. And so one of the neat things about kind of going through this and doing some examples like this is you can kind of start to predict what would happen. Because you can compare, oh, hey, this isotope looks like this. I know that the stable isotope looks like this. Well, if it's above, it's going to act one way. If it's below, it's going to act a different way. If it's, bigger than bismuth in terms of its atomic number, alpha decays are going to happen somewhere along the line as well. All right, any questions about the nuclear reactions or about, any of these kinds of little directions that we can go off of this? All right, so try one here on your own. We've got the neutron bombardment of technetium-98. We know we're getting an alpha particle. What's the other radioactive material? So let's take a couple of minutes and see if we can figure that out. It's an easy thing to forget, especially when we look at these, that there are two particles on the left-hand side, not just the one. Now, if you lost sight of that and ended up with niobium-94 as a result, that's okay. That's an easy mistake to correct, and it's an easy mistake to make. But just keep in mind, if you've got multiple things on the one side, you got to account for both of them. All right, any last questions out of this section? Okay, so the last thing that we want to talk about for today is just how do we measure radiation? And so the primary way that we measure radiation is using a Geiger counter. And I'll try to remember to bring one on Thursday, just so that you can kind of see what it looks like and how it works. But basically how a Geiger counter works is it actually can detect all forms of radiation, not just beta and gamma. But what happens is it uses the interactions between those particles and its electrodes to monitor when ionization is taking place. Remember, radiation is ionizing energy. It's going to strip electrons off of things. Well, if you put those electrons in a current, for example, that current would be detected by an instrument, in this case, the Geiger counter itself. So based upon how many interruptions to the current are being monitored, you can get an idea of how much radiation is in the area. Where do we tend to see radiation the most often? Well, it's just in our ordinary daily living. We can get, so REMs, which are one of the units of radiation, help us to measure how much dosage we have. Radiological equivalent men. So what we can see, this is the annual levels here. On a yearly basis, from minerals in the ground, you'll get a rough dose of about 20 milligrams of radiation. That's about as much as you would get for a dental x-ray. So again, we're not talking about a whole lot here. Now, a Geiger counter would pick up that radiation, but again, it's not a significant amount. The other places where we can get similar kinds of radiation, basically anything that uses, radar systems, so airfare, we can get it from that. We can get it from cosmic rays, so just the natural radiation coming from the sun. From building materials, that's actually the most common place where we can get it. This radon value here, EPA wanted to put a little tag on that. It varies very, very much based on where you live and what your house's foundation is, what kinds of minerals are natural to your environment. A lot of things factor into that. Of what? So radon is the product of the nuclear decay of radium. So right. No, so I'm gonna plead ignorance on what exactly it was in Brown County that was leading to that particular warning. But what I would say is it would seem highly unlikely that it's a decompositional product, considering that most things that are decaying are carbon based, and it's a long leap from atomic number 6 to atomic number 86. Things tend to break down, they don't tend to build up. Yeah. So that would be related to, more than likely, just the natural primary issue there is it's airborne inhalation as opposed to, but what you're getting from radioactive materials there is more than likely a product of the substances that are in the tobacco leaves, the substances that are in the nicotine, and just the naturally occurring radiation just coming from the fact that there are radioactive isotopes of those elements. You're just exposing your body to a greater percentage of them. And you're also inhaling them as opposed to letting them just float around you. All right, last bits of business here. Radiation sickness, largely based upon the dose of radiation that you receive. One way of marking dosage in terms of lethality is something called LD50. LD50 stands for lethal dose, 50% of the population. And so what that refers to is, in the case of radiation, this would be how much radiation would you need to be exposed to where half of us would die from. Now, LD50 can also be applied to other toxic materials as well. But since we're talking specifically about radiation, we would talk about dosage in terms of REMs as opposed to things like grams per kilogram of body mass or something like that, which is ordinarily what we think of when we think of toxicity. You know, this was brought up to me the other day. You ever wondered why a cockroach can survive pretty much anything? Look at the lethal dose of radiation for it compared to that of a human. The LD50 for humans is about 500 REMs. For an insect, it's about 100,000.
Is it because of, well, no, it's not because of size, because dogs are generally smaller than humans. Yeah.
I don't have a great explanation for you. I would say it probably has to do, at least in part, with like just how their anatomy is, the exoskeleton, providing some additional barriers. But that would be conjecture on my part. I would not be able to say that with any kind of certainty. And that's where we'll stop. So on Thursday, we're going to pick up the last 3 sections of this chapter, starting with half-life, which we've mentioned a couple of times, but we're going to get into more deeply and talk about kind of some calculations, some real simple ones, as simple as the ones we did today, for that kind of thing. Have a good day.